He was born in a Siberian town where winter lasted half the year and science felt distant, almost unreal. After his father died, he and his mother made their way to St. Petersburg by cart, with almost no money but an iron resolve to study. He taught with fire, wrote through the night, argued with academicians, rejected titles, and one day dreamed of something that would change science forever: order hidden inside chaos. That is how the periodic table was born. In this video, we'll tell the story of how Dmitry Mendeleev went from a provincial boy to a thinker capable of predicting elements that had not yet been discovered, how his fascination with oil, air, and measurement became part of a scientific revolution, why he refused to become a minister, and how his table outlived whole eras, turning into a universal language of matter. Suggest topics for new videos in the comments and subscribe to the channel. Sleep stories are posted here every day.
Childhood in Tobolsk, the roots of a hunger for knowledge. In early February 1834, in Siberian Tobolsk, amid endless snow-covered plains, the 17th and youngest child was born to Ivan Pavlovich Mendeleev, director of the provincial gymnasium, and his wife Maria Dmitrievna. The boy was named Dmitry. No one could have guessed that this name would one day become a symbol of scientific reason, determined to uncover the hidden order within matter itself. Dmitry's father, Ivan Pavlovich, taught philosophy. He was a widely read educator and a committed champion of enlightenment. He often read aloud to his children and loved to reflect on the nature of things. In that atmosphere, the boy's curiosity woke early. Dmitry later recalled sitting at his father's feet, not always understanding the words, yet sensing the rhythm and meaning of thought. But the family's steady life soon broke apart. When Dmitry was about 3, his father began to lose his sight. The illness moved quickly and relentlessly until he became completely blind. His career ended and the family lost its only stable income. Maria Dmitrievna showed extraordinary resilience. Raised in a merchant family, she had learned hard work from a young age, but now she faced an almost impossible task: feeding a huge household and giving the children at least a basic education. She did not surrender. On the contrary, in those difficult years, a firm belief hardened in her. Her youngest son needed a path into science. To make that possible, she decided to revive a glassworks that had once belonged to her family. The factory in the village of Oremzian near Tobolsk had fallen into ruin. Despite debts, a lack of skilled workers, and widespread economic chaos, she restarted production. Dmitry spent many hours there, watching molten mass become clear glass, seeing flame shape form, witnessing fire and sand unite into a substance that could be measured and understood. Later, he wrote that it was there he first began to think about the nature of matter and how regularity can emerge from apparent disorder. Still, the factory's income barely kept them afloat, and provincial schooling could not offer deep knowledge. So Maria Dmitrievna chose an act that, even by the standards of the time, bordered on madness. In 1849, when Dmitry was 15, she decided to take him to the capital, to St. Petersburg. The journey from Tobolsk to St. Petersburg took months and crossed thousands of versts through rivers, swamps, and impassable roads. They set out in winter with horses and relay carts, without companions, without money, without guarantees, just mother and son. Snowstorms and blockages stretched the road to nearly 3 months. They crossed the Urals, passed through Vyatka, Yaroslav, and Vologda, and finally arrived in St. Petersburg in spring, exhausted but alive. The first weeks in the city were the hardest. They had no money at all. They stayed with distant acquaintances and sometimes relied on chance lodging. Dmitry lacked the formal certificate needed for admission, but Maria Dmitrievna secured an audience with the director of the main pedagogical institute. According to one account, she brought a letter asking that her son be allowed to sit the entrance exams. Mendeleev later remembered he was permitted to try as an exception, as a chance. He passed.
It was the climax not only of his childhood, but of years of struggle, will, and a mother's devotion. Dmitry became a student at one of the country's best institutions. From that moment, he began a road that would lead not only to discoveries, but to the inner architecture of the world. His Siberian childhood ended not in a warm room or behind a school desk, but on a journey that spanned half a country. In the furnace of trials, in the shadow of factory kilns, and among glass molds, where science first touched his soul. St. Petersburg, a road through cold and poverty. In the spring of 1849, after a punishing journey of many months, Dmitry Mendeleev arrived in St. Petersburg with his mother. The city met them not with kindness, but with the chill of cobblestone streets, damp air, and the indifference of officials. No home, no money, no familiar faces, only hope, maternal determination, and a quiet yet indestructible hunger for knowledge. They managed to obtain permission for Dmitry to take the entrance exams for the main pedagogical institute, one of the few places where education was free. He endured the trial and was admitted. A new stage began. It was the life of a poor student in a dormitory, poorly fed on thin porridge and bread, yet greedily absorbing every fragment of learning. The dorm rooms were cold and damp. Windows were sealed with paper to stop drafts, though it barely helped. Dmitry owned little clothing, a worn, thin overcoat and scuffed boots. In letters to family, he did not complain, but classmates later recalled that in winter he slept in his coat, and in lectures often shivered from the cold. In those years, his health began to fail. Constant chill, hunger, and exhaustion took their toll. He developed tuberculosis. Doctors gave a bleak diagnosis and insisted he change climate. At the end of the winter of 1850, Dmitry was sent south to Crimea, first to Simferopol and then to Feodosia. There, among sun, sea air, and relative calm, he spent about a year. The illness receded, but the thought of death touched his mind for the first time. Even away from the institute, he lost no days. He read incessantly in Russian, French, and German, compared scientific articles, made notes, and thought. Later he recalled that it was in Crimea he first sensed that behind the diversity of phenomena there was something common, a law still out of reach. When he returned to St. Petersburg in 1851, he resumed his studies with doubled energy. Illness did not weaken him, it tempered his will. He decided that if life had granted him another chance, he would use it fully. He studied with fierce focus, worked nights, labored in the laboratory, and ran experiments. He was especially drawn to chemical processes, how substances interacted, how states changed, why reactions followed patterns. He earned money through private lessons and occasional translations. Still, there was never enough. At times he lived on tea and dry bread. One story claims he survived for a week on a single loaf and 2 mugs of boiling water because he refused to spend money saved for textbooks. He bore these hardships without complaint. His concentration was so intense that students and professors began to respect him despite his awkwardness and reserve. Gradually, the shape of a researcher appeared, not only a diligent student, but someone able to see the general through the particular. He asks questions others did not ask. Why are some gases lighter than others? Why do some metals react instantly while others only when heated? Why do the properties of certain substances repeat with such striking regularity? The Institute's laboratory was modest, but it was equipped. There he first conducted experiments on his own, measured densities, analyzed solutions, and recorded observations. What fascinated him was not the reactions themselves, but the inner regularities that governed them. The future system was being born, not yet formulated, but already felt instinctively. Teachers noted his unusual meticulousness. He did not merely complete tasks, he checked formulas, recalculated experimental data, searched for errors even where none seemed to exist. One instructor said, "This Mendeleev doesn't just want to know, he wants to understand." By graduation, in 1855, he was recognized as one of the Institute's best. He was offered a teaching post at a provincial gymnasium, but refused. He wanted not the classroom, but the laboratory. He wished to remain in St. Petersburg, where there were libraries, chemical cabinets, and above all, a scientific environment. With professors' support, he was allowed to stay at the institute to prepare for a professorship. In these years, the person he would become took final shape, someone for whom the search for patterns was a life's purpose. Poor, ill, often alone, yet inwardly sturdier than many, he carried a structure as resilient as the one he would soon discover in matter itself.
The making of a scientist, from teacher to thinker. In the mid-1850s, after graduating with distinction, Dmitry Mendeleev stood at a crossroads. Some classmates went to teach in provincial schools, others looked for bureaucratic posts, and some considered abandoning science as a hopeless path. Mendeleev chose a road that promised neither comfort nor security. He stayed in St. Petersburg and dedicated himself to research. He continued his work at the institute and later gained the opportunity to train abroad. In 1859, he went to Germany, then one of Europe's great scientific centers, to the University of Heidelberg. Young chemists from around the world gathered there to learn from Robert Bunsen, Gustav Kirchhoff, and other leading minds who pursued experiments with a precision previously unimaginable in chemistry. Mendeleev quickly realized that serious work required more than attending lectures. He rented a room and built a small laboratory at home, a spirit lamp, flasks, scales, reagents. In those sparse conditions, he began experiments on the expansion of liquids, evaporation, densities, and solubility, phenomena that seemed familiar, but under close study proved far less predictable than people assumed. He focused especially on mixtures, particularly solutions. The topic looked technical and secondary, but Mendeleev approached it systematically. He gathered empirical data, sought patterns, and tried to express mathematically what had previously been described only qualitatively. His paper on alcohol solutions was published first in a German journal and then in Russia, becoming his first recognized scientific contribution. He spent about 2 years in Germany, befriending many European scientists, attending conferences, reading in German, French, and English, and keeping up an extensive correspondence. He followed new publications and methods closely, yet developed his own approach. Abstract constructions for their own sake held no appeal for him. He believed in observation, experiment, and structural thinking grounded in reality rather than speculative schemes. Returning to Russia in 1861, he defended a master's thesis on the interaction of alcohol and water. The work stood out not only for experimental rigor, but for its attempt to grasp hidden laws inside the most ordinary chemical processes. Soon he was invited to teach at the St. Petersburg Technological Institute and then at St. Petersburg University. At the university, he immediately stood apart. His lectures were lively and coherent, free of needless dogma. He spoke without notes, moved smoothly from theory to practice, drew examples from the history of science, and sometimes added fresh anecdotes from his correspondence with European colleagues. Students came to him not from fear, but from genuine interest. He demanded precision, yet encouraged independent thought and unconventional conclusions. For him, teaching meant not only transmitting knowledge, but cultivating a scientific way of seeing the world. Alongside teaching, he kept experimenting. He studied gas pressure, liquid behavior, specific weights, evaporation, and other parameters that illuminate the nature of matter. He built tables of measurements, calculated relationships, and constructed logical chains. All of it ran alongside accumulating theoretical generalizations that would later become the foundation of his central work. He developed a distinctive scientific style. He was dissatisfied with observation alone and never replaced experiment with speculation. He could see the universal behind the particular without losing the concrete. His method was synthetic, combining empirical evidence and theory, quantitative analysis and qualitative observation, rigor and intuition. He studied not only chemistry, but also physics, mathematics, geology, and the philosophy of science.
He corresponded with historians, debated colleagues about truth in science, advocated for reforms in teaching, and remained deeply engaged in the intellectual life of his time, yet kept a rare focus on the world's underlying laws. Already then, while studying substances, he began to notice that certain elements behaved similarly. He recorded observations, noted repeating properties, and compared atomic masses. It was not yet a theory, not yet a system, but a direction of thought pointing toward a simple idea. Nature is not chaotic, but structured, and that structure can be understood. By the end of the 1860s, Mendeleev was not merely a lecturer, but a recognized thinker, whose voice carried both in the university and in academic circles. His articles were published, his lectures drew crowds, and his chemistry textbooks became desk companions for young scientists. Yet, the main discovery of his life was still ahead, gathering itself in silence.
A dream that changed the world, the periodic table. Mendeleev was already an established scholar, a professor at St. Petersburg University, the author of works in physical chemistry, and a methodologist who reflected on science's role in education. He taught, wrote, experimented, and engaged in scientific debates. But one unresolved question returned again and again, troubling many chemists of the era. Do the properties of the elements follow a law, or are they merely a chaotic collection? By then, science knew roughly 60 elements. Their number grew with every decade, yet there was no system that could reveal their relationships. Researchers tried to classify them by atomic mass, by valency, by external similarity. But every scheme was fragile. A newly discovered element or a corrected measurement could collapse the whole structure. Iodine did not fit in one system, tellurium in another, lead or thorium in a third. Mendeleev felt that beneath the variety of chemical and physical properties, there had to be an inner unity. He believed nature could not be meaningless. If substances have properties, there must be an order governing those properties. For him, this search was not an intellectual game, but the task of a lifetime. At the same time, he was working on a major textbook, Principles of Chemistry. It was not a compilation of facts, but an attempt to present chemistry as a coherent, structured science. Yet when he reached the chapter on the elements, he hit a wall. How could he present the whole chemical world in a way that was not only easy to memorize, but faithful to nature itself? He decided to begin not with prose, but with a table. He took cards and wrote one element on each, listing its atomic mass, density, valency, typical compounds, the properties of its oxides and acids, melting and boiling points, thermal and electrical conductivity. Then he began to shuffle the cards, grouping elements by similar behavior, comparing their masses, searching for repeating structures. He spent hours at it, then days, then weeks. Accounts describe him in his office surrounded by heaps of cards, papers, and sketches. He crossed things out, rewrote them, drew fresh tables, refusing to stop even at night. A servant would bring tea that cooled, untouched, while he, frowning in concentration, kept moving the elements, as if the right order might suddenly reveal itself. He sensed the key was not in the properties themselves, but in their repetition. The breakthrough was not to reduce properties to a single formula, but to arrange elements so that properties began to recur at regular intervals. He lined them up by increasing atomic mass and discovered that after certain steps, familiar traits returned. Lithium, sodium, potassium, fluorine, chlorine, bromine, calcium, strontium, barium. A rhythm appeared, a structure inside what had looked like disorder. Later, Mendeleev recalled that at some point he fell asleep at his desk and saw in a dream a table in which all the elements sat in their proper places. He awoke and immediately sketched the scheme on paper. He treated the episode without mysticism. The answer had been earned through long, exhausting work, and the dream simply helped gather everything into one image.
But for later generations, the dream became a symbol of scientific illumination, that rare instant when truth seems to arrive whole. In early spring of 1869, he presented his system to the Russian Chemical Society. His report, an attempt at a system of elements based on their atomic weight and chemical similarity, stated the core principle. When elements are arranged by increasing atomic mass, their properties repeat periodically. The table was not only horizontal, but vertical. Elements with similar properties formed columns. More boldly, he left empty spaces. He argued that science had not yet discovered all the elements, but those missing ones must exist. It was an audacious move. He did not merely classify the known, he predicted the unknown. The first reactions were restrained. Some colleagues were intrigued, others skeptical. The table looked elegant, but many doubted its practical value, especially the blank squares. Yet a number of scientists recognized a powerful analytical tool. In education, its impact was immediate. Mendeleev insisted the table be printed separately as a wall chart. It spread through universities, laboratories, and schools. Students began to study chemistry not as a random heap of facts, but as a logically organized science. Meanwhile, he continued finishing Principles of Chemistry. The first volume appeared in 1870, written with clarity, vivid examples, and above all, a unified concept. With each new edition, he refined the text, added data, sharpened definitions, and expanded interpretations. For Mendeleev, the table was not a final point. He kept testing it, correcting atomic masses, arguing with rivals, adapting to new discoveries. But even at its first publication, he knew he had done more than offer another classification. He had drawn a map in which nature revealed order, and humanity gained an instrument to understand it.
Science's prophecies, elements that did not yet exist. When Mendeleev published the first version of his periodic system, readers were struck by its symmetry. Elements rose by atomic mass and properties repeated at intervals. Yet the truly revolutionary feature was less obvious: the empty cells he left deliberately. He insisted those spaces belonged to elements not yet known, but destined to be discovered. More than that, he predicted their properties in advance with a precision that still astonishes. He gave them provisional names: Eka-aluminium, Eka-silicon, Eka-boron, Eka-manganese. The prefix Eka, borrowed from Sanskrit and meaning one, indicated a position one step below a known element in the same group. From periodicity, he derived atomic mass, density, chemical activity, the nature of compounds, and even physical traits of substances no one had ever held. He predicted, for example, that Eka-aluminium would have an atomic mass near 68, a density around 6 grams per cubic centimeter, an amphoteric oxide, and a relatively high melting point, and that it would form salts similar in appearance and crystalline structure to aluminum salts. Many chemists admired the elegance, but treated the predictions cautiously. Some of his placements also clashed with existing measurements. He insisted, for instance, that tellurium belonged before iodine, even though their measured atomic masses suggested otherwise, arguing that atomic mass alone could not be the sole key to order. Then nature began to answer. In 1875, the French chemist Paul-Émile Lecoq de Boisbaudran discovered a new element while studying zinc ore spectra. He named it gallium. Its atomic mass was close to 69, its density about 5.9 grams per cubic centimeter, and its chemistry amphoteric, matching Mendeleev's predicted Eka-aluminium astonishingly well. Mendeleev published a point-by-point comparison, emphasizing that the discovery confirmed not merely an element, but the system itself. 4 years later, Swedish chemist Lars Fredrik Nielsen identified scandium, filling another predicted gap. and in the mid-1880s, German chemist Clemens Winkler discovered germanium while analyzing the mineral argyrodite, matching Mendeleev's predicted eka-silicon, a semimetal with an atomic mass around 73 and mixed metallic and non-metallic properties. By the 1990s, the most famous blank spaces had been filled, and filled with an accuracy that transformed the scientific mood. The table was no longer just a teaching convenience, it became a predictive model capable of guiding research. Mendeleev was invited to international congresses. His work was translated widely. Where doubt had once ruled, admiration spread. Yet Mendeleev did not celebrate himself as a prophet. In correspondence, he insisted he had not found the elements, only indicated where they should be. If they appeared there, the table was right. For him, the triumph was the confirmation of a logic drawn from matter itself, not from fashion or speculation.
Beyond chemistry, oil, air, and Russia's future. After the periodic system gained international recognition and the predicted elements were discovered, Mendeleev did not stop. His mind, trained to seek order, turned increasingly to problems beyond academic chemistry, economics, industry, and the modernization of Russia. He did not separate theory from practical benefit. To him, they were two sides of one duty, serving progress. One of his first major concerns was oil. In the mid-1870s, extraction in Baku and the Caucasus expanded rapidly, but refining remained primitive. Oil was often burned directly or wasted because people did not know what to do with it. Mendeleev traveled to the Caspian region, inspected fields, spoke with workers, analyzed samples, and recorded losses. What he saw shocked him. He famously compared burning oil as fuel to burning banknotes in a stove. He became a leading voice urging reform. Oil was not merely fuel, but chemical feedstock capable of yielding dozens of useful products, from kerosene and lubricants to dyes and explosives. He argued for refineries, engineering training, improved distillation science, and local processing instead of exporting crude oil. Many of his ideas were adopted, and by the 1890s, more modern facilities appeared in Baku. Another passion was aeronautics. He studied balloons at a time when few in Russia took the idea seriously. He explored how aerostats could serve scientific observation, military reconnaissance, surveying, and communication. He calculated lifting forces of various gases, examined thermal conductivity and density, and even developed design considerations for balloon envelopes accounting for temperature and pressure in different regions. He argued that air navigation had a future and that Russia, with vast, hard-to-reach territories, could lead the way. Equally important was metrology, the science of precise measurement. Appointed head of Russia's main chamber of weights and measures, he pushed for standardized units, the adoption of the metric system, and uniform measures of length, mass, and volume. He personally checked standards, wrote procedures for verification workshops, and lectured to surveyors and merchants. He believed that without precise units, there could be no fair trade, no industry, and no science. He also wrote on education, economics, and statistics, calling for university reform, technical schools, expanded access for women, and curricula that reduced Latin and strengthened physics and mathematics. Again and again he insisted that without science, Russia could not become a great power, and that educational backwardness would inevitably produce political and economic weakness. Conflict with power, the price of principle. By the 1890s, Mendeleev was not only a world-famous scientist, but a public authority. Yet in a country where academic life increasingly fell under administrative control, an independent thinker was bound to collide with the system. He began teaching at St. Petersburg University in the mid-1860s. His lectures filled halls. He taught chemistry as a way of thinking, defended experimental practice, expanded laboratory training, and argued for reforms that would connect science with industry. But by the 1880s and 1890s, state interference in universities intensified. Restrictions on student meetings, tighter oversight of curricula, and demands that professors follow approved programs without deviation. For Mendeleev, who valued intellectual freedom, this was intolerable. After student unrest and heavy-handed policing, he defended his students. He did not endorse disorder, but openly argued that repression only deepened the problem. He submitted his resignation, explaining he could not work in an atmosphere of pressure and mistrust. The decision caused an uproar. Students petitioned, colleagues appealed, newspapers debated. He did not change his mind. For him, a university existed to seek truth, not to function as a bureaucratic department. A teacher deprived of free judgment, he wrote, loses dignity and becomes a mere announcer of a program. After leaving, he devoted himself to metrology, where results were concrete and less dependent on ideology. His stance was political in a deeper sense. He insisted that a scholar must be independent, that truth outweighs rank, and conscience matters more than career. Offers of posts and honors came with conditions, and he refused them. A particularly painful episode involved the Imperial Academy of Sciences, which never elected him a full member despite his achievements. Officially, the reason was a lack of classical formal education, but many contemporaries saw intrigue and envy. He took the rejection with outward calm, though not without bitterness. Still, he continued writing, consulting, and supporting younger researchers. For many, he became not only a great chemist, but a moral benchmark. A legacy that outlived eras. In the late 19th century, after leaving university teaching, Mendeleev remained active in science and public life. He followed developments in physics and industry, wrote about oil and coal, and proposed plans to modernize transport and production. One notable contribution was his participation in the concept of an Arctic icebreaker. He believed Russia must develop the Northern Sea route and contributed ideas on hull shape and mass distribution that were used in building the first Russian Arctic icebreaker, Yermak, launched in 1899. In the early 20th century, his health deteriorated, but he kept working. In 1900, he oversaw the Russian exhibit at the Paris World's Fair and received the French Legion of Honor. By then, the periodic table had already proven its brilliance. Letters arrived from across the world, sometimes addressed simply St. Petersburg, to the scientist who predicted elements. He once said he was glad the table lived on, but he did not need titles. If it was correct, it would be accepted without him. In his final years, he tried to expand the table to account for uranium and other elements he believed would be found later. He speculated about substances beyond contemporary understanding, about the ether, and about the structure of the atom, sensing that chemistry stood on the brink of revolution. In the winter of 1906, he weakened severely, but continued writing. On his desk until the end lay a draft table with blank cells, places reserved for elements still undiscovered. On 27 January 1907, Dmitry Ivanovich Mendeleev died in his apartment on the Moika embankment. At his funeral, people carried a banner bearing the periodic table. One student held a sign, "He brought order to chaos." After his death, his work entered a second life. Noble gases were added in the early 20th century, later the lanthanides and actinides. Quantum physics explained the table's structure through energy levels, orbitals, and electron shells. An element later received the name Mendeleevium. Today, the periodic table is far more than a classroom poster. It underpins the sciences of matter, from biochemistry to astrophysics and materials science. It hangs in NASA laboratories and on the walls of rural schools, a symbol of the order hidden in nature. Mendeleev's legacy is not only a table. It is the idea that truth yields to reason, that the world is knowable, and that a scientist's labor can be more than contemplation. It can be the active building of a new reality. He left behind a structured staircase from hydrogen to super-heavy elements, from observation to prediction, from chaos to order.